So this experiment is called Ohm's law. So we're looking at the relationship between voltage, resistance, and current. Okay, and we're also testing the equations for the effective resistance of resistors connected in series and resistors connected in parallel. Okay, so we're going to start with our basic setup. So we have our voltage source. We have these 1.5 volt batteries, and we can choose how many of them to have in our circuit. So we can choose 1.5, 3, 4.5, or 6 volts for our power, and we're going to measure the current by running it through the multimeter, now in current sensing mode. Okay, so remember that when you're measuring the current, you actually have to have the multimeter be a part of the circuit. Okay, so that's why I have it wired up so that from the positive terminal it goes through the multimeter. We're going to connect this last connection. It'll go through the resistor and then back to the negative terminal of the battery. Okay, so we're going to see how the voltage depends on how the current depends on the voltage, right? We know Ohm's law says that for most objects, including these resistors, you have a linear relationship, V equals IR. So if you solve for I is V over R. So the current is a linear function of the voltage, and to find it, you just divide the voltage by the resistance. Okay, so we're going to connect this first resistor here. So you can read off the colors. It looks like it's orange, orange, brown with the gold tolerance label. Okay, so you can see what the labeled resistance is based on the colors. Okay, then we can connect the 1.5 volts first. Okay, we see we get a current of 2.53 milliamps. If we increase the voltage, we're going to get 3 volts. We get 7.3 milliamps. 4.5 volts, we get 9.5 milliamps, and then for 6 volts, we're getting 13.75 amps. Okay, so we can repeat this process using the different resistors, right? You can have different individual resistors, and you can see, you can plot current as a function of voltage, right? The slope of that line is going to be 1 over R. Okay. We also want to look at what would happen if we do resistors in series and in parallel. Okay, so we know that for the case of resistors in series, the effective resistance, right, if you would replace those resistors with a single resistor, that resistor should have a resistance equal to R1 plus R2 plus R3, right? This is the sum of how many resistors that you have, okay? Just to keep things straight, we're going to arrange the colors like this. The colors don't actually matter, it's just for convenience to help us keep everything straight. The order also doesn't matter. If you're arranging them in series, the order doesn't really matter, okay? Just have to make sure that we connect them in the proper sequence. So resistors connected in series means one after the other after the other. So the current has to, the charges have to go through one, then the other, okay? In this case, We've got our orange, orange, brown again. We've got our red, red, brown. And we've got our brown, green, brown resistors that we're connecting in series. Okay, as we know, the resistance for resistors connected in series is larger than the largest, right? Because now you're adding them together. Okay, so we're going to get a current of, when we have a voltage of 1.5 volts, now it's only 1.9 milliamps, right? Now I'm going to do 3 volts, we get 3.92 milliamps. 4.5 volts, we get 5.7 milliamps. For 6 volts, we get 7.63 milliamps. Okay? So this is for our situation when they are connected one after the other in series. Okay. The last part of the experiment is now we're looking at when they're connected, when they're going to be connected in parallel. This is a little bit trickier to do, but the idea is that you want to connect it so that all of the right-hand side of the resistors are connected to the same voltage, and all the left-hand side of the resistors are connected to the same voltage. And we do that with more wires. Okay, but we're going to have all of the red terminals for this are going to be connected to the positive terminal. All the black terminals, black sides are going to be connected to the negative terminal. And we're going to see how that affects the current. Now remember, for the resistors connected in parallel, now the current can go through one or the other, so the resistance is smaller than the smallest. Okay. Using our resistance formula for resistors, the equivalent resistor for resistors connected in parallel. Okay, so I'm connecting all the red terminals together, connecting all of the black terminals together. Now I'm connecting the black terminal to the negative terminal of the battery. Now I'm connecting the positive terminal. Okay, so now we see a much larger current, right? Even with just 1.5 volts, we're getting 11.25 milliamps of current, right? It's a much larger current because current can go through one or the other. Preferentially goes through the path of least resistance, right? But some current goes through all the branches. If we go to 3 volts, it's already 30 milliamps. 4.5 volts is 43 milliamps. And with 6 volts, we get 61 milliamps, okay? So this is a demonstration, right, showing you the relationship between voltage and current and the different configurations of resistors.